So, right, I'm Krishna. This is joined with Kevin, who's sitting there. And okay, so starting point for this, I think it won't surprise anyone here, probably anywhere, that the big way people get news about various issues now is content on social media, and particularly viral content on social media. And so an important question is going to be what goes viral and how does that affect what people end up believing? And a key feature of various types of social media platforms is what goes viral depends jointly on decisions being made by users and also platform algorithms. So let me say a little more about what we mean by that. What we have in mind is types of platforms, and I'll give examples in a moment, where users post various types of stories that contain some potential information on the platform. Platforms, like was just motivated in the last talk, don't show people everything that's been posted. They select some news feed that determines essentially a small sample of these stories that people end up reading or looking at. Users in various ways retweet or share or upvote some of these stories. We're going to condense this in the model into a single endorsement action. And then the platform algorithm determines how these endorsement actions, as well as a number of other characteristics, affect what future users see in their newsfeeds. So of course, these algorithms are large and complicated, but what we see as a key platform design choice that we're going to look at in a more stylized way is how much do you show more popular content that's been endorsed a lot or is going viral versus other content that in our model is going to be random, but you can think of as being selected along other mostly orthogonal dimensions. And so what I'm going to tell you about today is an equilibrium model where users are interacting with and sharing news feeds, and where we're going to look at some trade-offs for learning between showing more viral content versus more random or unbiased content in news feeds. So before I get into the model, let me just give an overview of the main trade-off that we're going to find. And then I'll tell you about how we formalize that and some of the details on it. So the big question is going to be, how does showing more viral content in news feeds change learning outcomes? And it turns out that in some ways it can be helpful. It can be that if I'm showing people mostly viral content in their news feeds, then just a few stories can convey a lot of information. So as intuition for that, let's say that I go onto some community on a social media platform, like maybe Reddit, and look at the top few posts. If I know that those posts are likely to be at the top because they've been upvoted or shared by many people, then I don't just learn about the content of those posts and the experiences of the users who posted them. I also learn something about the broader opinion and potentially close to consensus in a larger community. And so the stories I see don't just contain the sort of informational content of their signal. If I'm able to understand this selection, I can also learn about other people's endorsement actions. In turn, that can tell me about other information or experiences that they may have. So this is an upside. I can learn a lot more potentially from a few posts. A downside, which you might imagine, is you can end up in sort of feedback loops where learning goes around. And so we call these misleading steady states. And what we show is this can happen even with rational users trying to share accurate content. And so the intuition behind these is that most of the content on the platform might be correct, but these incorrect stories can get shown more after we sort of wait for virality. After we think about the fact that the algorithm is mostly showing more popular stories. And this can self-perpetuate. People see incorrect stories, they end up believing the incorrect state, they continue upvoting incorrect stories. Again, it'll be intuitive this could happen if people are just mechanically following what they see. We're going to show this happens even if people are rational and trying to account for this in some way. So let me jump into the model. If you're in the first talk in this session, this is similarly going to be a sequential learning model. People are learning about an unknown state of the world, which is either positive or negative. Agents are arriving one at a time, seeing some content and deciding what to share. And they're going to each receive their own news story, which is just a signal about the state, which is binary and symmetric, so it matches the true state with probability Q and the incorrect state otherwise. And we're going to assume, it turns out this isn't too important, that they post their story SI on the platform. We think you could do sort of other assumptions about this. And when it's posted, it's going to start with a popularity score of 1. This popularity score is going to track how many times it's been shared or sort of more abstractly endorsed. They're also going to see a sample of case stories from other people. So a newsfeed of case stories that other people posted or shared. And I'll tell you in a couple of slides how this is sampled, but it can depend on the popularities of the different stories. And to make the inference sort of tractable, we're going to assume that they just see the realizations of these stories and not other information about them. And the other thing to mention is, well, we need to initialize the system so the first person has something to see, but you can essentially do this in any way, and our results will go through. Their choice then is going to be some number of these stories see to share from their newsfeed. Everything they share, the popularity score goes up by 1. And we assume that people want to share stories that match the state, so they get a utility of U, which is positive from each story that they share that matches the state, the utility of 0 from stories that don't match the state. And again, we see this as a benchmark where you would think people are doing something relatively conducive to learning, but we'll see learning can still go wrong. And just to give, okay, so this is most of the model. I'm going to give an example, but I want to say a word about it. I know some of these assumptions may feel stylized. A lot of the reason we're setting, if I had more time, I would talk about why we think they're reasonable assumptions about the world, but we're also setting it up in this way to be able to make analytic progress in a sort of class of models that often proves to be intractable. And so I'll say a little more about that when I get to the results. But let me just go through an example of what's going in the model so that you can see what's going on. So this is an example. I guess you can see the
Height control shows limits.
Right?
What's the more? Height meeting controls. There we go.
Thanks. Okay, so this is an example where each person is seeing 3 stories and picking one of them to share. So person 6, these are the first 5 stories that people got. Person 6 arrives, they see some sample of 3 of these, which might again depend on how popular they are. And they end up seeing 2 positive stories and 1 negative one. Their own sort of news story is positive. They have to decide which state is more likely. Maybe based on this, they decide that the positive state is more likely. And they decide to share one of the positive stories. Its score goes up by 1. Now it's more likely to be sampled by the next person. The next person arrives, gets a sample, decides what to share, and so on. And this is going to keep on continuing. And so the last part of the model to tell you is how do these news feeds actually get sampled? And what we're going to look at is a family of sampling rules parameterized by a variable lambda that says how much do you show more viral or higher popularity score stories versus more random stories. So every time we pick a story for the newsfeed, we're going to, with probability lambda, sample a story with probability proportional to its popularity. So in a way that selects higher popularity stories more. And with probability 1 minus lambda, just choose an unbiased random story out of all the stories that have arrived. And so higher lambda, we show more viral stories. Lower lambda, we show more random stories. And what we're going to be interested in is what happens on this platform if people are sharing in an optimal way or in a rational way as time goes on. And what does that mean for what people end up believing? And so to formalize that, we're going to look at equilibrium. People's strategies are just choices based on their observations of which stories to share. We're going to look at Bayesian-Nash equilibrium with some symmetry assumptions. And the way to think about the content of this is that equilibrium means that people are interpreting their news feeds in a Bayesian way and sharing the stories that are more likely to be correct given the Bayesian beliefs that they form. There's a lot of details that I can't go into about what that means, but this is the basic point. People are trying to share correct things and rational about the information. And we're mainly interested in what happens as the platform grows large. So I'm going to define a strategy to be a limit equilibrium if it's the limit of sequences of equilibria for societies with n agents or platforms with n agents as n grows large. So to understand what's happening at some equilibrium, I'm going to want to understand sort of the state of the platform. And it turns out the key statistic describing the state of the platform at a given time is what we call the viral accuracy. The viral accuracy after agent T arrives on the platform and decides what to share is the fraction of the total popularity score that's on stories matching the state. So this is asking when somebody has shared something, how often, or posted something, how often has it matched the true state rather than matching the incorrect state. So just to give a quick example of this, back to my newsfeed from before, let's say the state is positive here, then the positive stories have a total popularity score of 6, they've been shared more. The negative stories have a total popularity score of 3, that means the viral accuracy is 2/3. And so in this case, people are mostly sharing, although not only sharing and posting correct content. If the viral accuracy were less than 1/2, it would mean people are mostly sharing incorrect content. This viral accuracy is useful because it turns out it's going to converge almost surely on this system. So if you had an infinite number of agents sharing using any fixed strategy, which might or might not be equilibrium, the viral accuracy would converge to some steady state value x star. And so this is going to describe the long run accuracy of what people are sharing on the system. And it turns out that this converges, but it doesn't have to converge to a deterministic limit. So it could be that there's a positive probability of converging to one steady state, maybe where the viral accuracy is high, and a positive probability of converging to another one where the viral accuracy might be low. And we're going to distinguish these cases by calling a steady state informative if a random story in somebody's newsfeed is more likely to match the true state than not, and misleading if a random story in somebody's newsfeed is less likely to match the true state than the incorrect state. And so what we're going to want to ask is, at equilibrium, do we end up with only informative steady states, or do we also get these misleading steady states? To do that, we want to characterize the steady states that you end up at, and we do that as fixed points of this sort of natural function. We call this the inflow accuracy function, and essentially what it says is if the viral accuracy is x right now, the value of this function at x is the viral accuracy of the new stories that are getting shared in subsequent periods. So a little more formally, it's the expected fraction of the incoming popularity score on stories that match the true state. So a steady state intuitively is going to be somewhere where the new viral accuracy is equal to the current viral accuracy. So let me just give an example of this. And I'm going to give this example under a strategy that's going to turn out to be important for understanding equilibrium, but that doesn't a priori have to be optimal. And that's what I'll call majority rule. And what this majority rule does is it just says, look at your newsfeed and follow the majority of the things that you see there, and only use your own signal, your private signal, if you need to break ties. So intuitively, this is a good rule if your newsfeed is informative, and at least as informative as your private information. Not such a good rule if you think your newsfeed is probably misleading. And here's this inflow accuracy function. This is saying if you have the current viral accuracy on the x-axis, what viral accuracy should you expect in subsequent periods? And what we can see here is there's two sort of stable steady states of this thing. There's one in the top right where things are good, the viral accuracy is high, people are mostly seeing and continuing to share correct content. But there's another one in the bottom left where the viral accuracy is below 1/2, and so mostly people are sharing wrong content. And the intuition for this is that these false stories are becoming self-sustaining. Most people see a newsfeed that has mostly false stories, even though most of the stories on the platform are true, because the false stories are more popular. And then this majority rule just mechanically shares the things that it sees in the newsfeed, the majority of false stories that it sees, and so the viral accuracy remains low. The wrong things are mostly getting shared. And again, this is happening mechanically here, but I'm going to show you in 2 slides it still happens if people are rushing. So to state that more formally, I need one more definition, which is what I'll call a critical virality weight, which is the virality weight, the level of this parameter lambda, where we get these misleading steady states. So it's the least virality weight where this simple majority strategy has a misleading steady state. And so what this example is showing is if you don't weight by virality, if you just show people an unbiased sample of signals, you're not going to get this misleading steady state. The viral accuracy on the platform isn't going to matter for what people see. And so if lambda were 0, this curve I'm graphing would be flat. But as I show people more viral content, this starts to get more and more closer to being possible. And then there's some level where you start to get these misleading steady states. And so what our first result about equilibrium says is that at this critical threshold, we start to get these misleading steady states. And it actually turns out that it happens in a discontinuous way, where the probability of converging to a misleading steady state jumps from 0 to something strictly positive. I don't have time to go into any detail on that, but that was a cool, surprising result to us that I'm happy to talk about more if you're interested. But what I can tell you now is formalizing this. If we're below this critical threshold, there's a unique limit equilibrium. And this equilibrium has a unique steady state that's informative. So if we're below the critical threshold, if you're not showing too much viral content, then you don't get these misleading steady states. There's nothing going sort of systematically wrong. On the other hand, at or above the critical threshold, every equilibrium has at least one misleading steady state. So under any equilibrium behavior, there's a positive probability of ending up with one of these learning types. So this is formalizing this message from the beginning that platforms that push viral content into news feeds generate misleading steady states. Something else I want to point out about this is it's reducing understanding equilibrium behavior, which in general is a quite complicated object. It depends on this distribution of steady states of this stochastic process that doesn't have any closed form characterization. But analyzing this majority rule is much simpler. This is just a polynomial. Object, and so we can qualitatively understand these complicated equilibria by looking at a much simpler and sort of more accessible strategy that tells us about its qualitative properties. Let me quickly spend my last 45 seconds telling you about the other half of the trade-off that I told you about, which is that increasing lambda can help the stories you see aggregate more information. And one version of this is if we're below the critical threshold, then higher lambda is better. So as we increase lambda, the steady state in the top right moves up. So what this is saying is for lambda below the critical threshold, when we don't have misleading steady states, showing more viral content makes the information people see more accurate. So this is formalizing the message that platform algorithms that weigh virality more heavily can help aggregate more information. And so more formally, as we increase this parameter lambda, the newsfeed stories people are seeing become more accurate indicators of the true state. So we talk more in the paper about various sort of consequences of this for platform design, but I'm basically out of time. So I'll just wrap up by saying these two results we think of as a trade-off for increasing lambda, where it can help the platform aggregate more information, but can also help create what you might think of as sort of informally a systemic risk of these misleading steady states where most people end up seeing wrong content and forming wrong beliefs. I'm out of time, so thank you very much.